have a table of data that tells me the total sales in millions of dollars as a function of number of years since 1980. So, for example, in 1980, that would be 0 years since 1980, so this is 1980 here, sales were $1.19 million. So please try to remember the units of the problem. The first problem I'm going to do is to determine the average rate of change, which in mathematics that is the slope between 2 points. So determine the slope between the point corresponding to 1985 and the point that corresponds to 2005. So first of all, I have to identify my 2 points, and when you do that, you should always include units. First, we identify that 1985 is 5 years since 1980. So this is 1985 information here. That's 1 point. In fact, let me write that down as a point. 5 years since 1980, comma, the output is 1.4, and let me write just MD for $1 million to make it short. And then the other year in question is 2005, and you're to determine that 2005 happens to be 25 years since 1980. Right? It would take 20 years to get to the year 2000, and then 5 more for 2005. So this right here, 25 years after 1980, would be the year 2005. It turns out, as far as average rate of change is concerned, I only need those 2 points. Right? To find slope, you only consider 2 points. So my second point would be 25 years, comma, 2.12 million dollars. Notice I'm putting units in here. So if you remember the definition of slope, it involves defining 2 x-y pairs. In fact, there's 2 of them. So we typically call this x1, y1, x2, y2. You should know in general, since we tend not to use x's and y's in applications in math, that in general you could think of slope, instead of change in y over change in x, you can think of it as change in your output variable, regardless what it is, because I wouldn't use y for sales, I'd probably use s. And then it's over change in input, and again, I probably wouldn't use x for time, I'd probably use t. So this would be t, and this would probably be s of t or something, and my slope would be change in s of t over change in t. So this is going to be y2 minus y1. I'm going to try to find the change in the sales. Remember, my output is sales over change in my input, which is time. So I would have 2.12 minus 1.4, but notice I'm going to take the time to simply write MD, because it's obvious right now that this number and this number is in $1 million, because I'm getting these numbers right from the chart, and it tells me right here. So this is a convenient place to put the units. And then my change in X, my change in time, was I ended at 25 years, and I'm subtracting off my starting at 5 years, and notice I'm going to put the units right here. So in the end, what we're going to get is millions of dollars per year, and you've probably heard me say this before if you've watched any of my videos, that the division symbol here in slope, you should pronounce that as per instead of divide by. So I'm going to type in 2.12 and subtract 1.4, and I get that my numerator is 0.72. I'm going to do this in steps. So I get this as $0.72 million. Notice that I'm not ever going to shy away from writing the units. 25 minus 5 is 20 years. So this is the average rate of change. The fact that it's change in sales, and this is a positive number, positive change means increasing. So if my sales increase by $0.72 million, then that means that time must have increased by 20 years. So this is change in time down here, and this is change in my output, which is sales. If time changes by 20 years, meaning 20 years from now, my sales will increase by $0.72 million. So you have a choice to convert this into dollars as opposed to $1 million right now, or leave it the way it is. I mean, this is actually the average rate of change. It's just some feel the need to convert that into what's called a unit rate and tell me what's going to happen on average over a 1-year period as opposed to a 20-year period. So if you want to do that, you take your previous answer of 0.72 and divide by 20, and that would be giving me the amount of increase in sales over a 1-year period. It would be a little more difficult to explain because the answer is $0.036 million per, right? We could put the division symbol, per 1 year now. So I basically simplified this down to, I took this and I left the units millions of dollars per year. It's just my calculator said that this number is equivalent to 0.036, but the units would still be in millions of dollars. And since I simplified it to a single number as opposed to a fraction, if you wanted to put a number down there to represent the change in years, it would have to be the number 1 as not to change the value of the slope. So you could say that sales are increasing $0.72 million over a 20-year period, or if you felt the need to convert it into a unit rate, which is per year, then sales would increase $0.036 million. I'll show you how to convert a number from million dollars to just dollars. You always can go by the number of zeros in the number corresponding to these words. So since the word 1 million represents this number here that has 6 zeros, what that means is you can convert from $1 million to dollars by moving the decimal to the right 6 times. Or you can think of it as you're multiplying by a million. But when you multiply by a million, it moves the decimal over 6 times. So I'm sitting at 0.036, and I want to convert it from $1 million into dollars. I will move the decimal to the right once, twice, 3 times puts me to the right of the 6. If I do it a 4th time, it introduces a 0 there, a 5th time another 0, a 6th time another 0. So if the decimal was here now, your number would be 0.036,000, and that would be kind of meaningless to put a 0 in front now. So I'm going to omit that 0 and just write 36000, and remember that this was per year. So if you remember, the $36,000 per year is just the average rate of change. So it's just an average, but it is how fast sales are changing. And the fact that the slope came out to be positive means that sales are increasing, right? Positive change means increasing. So to form a sentence, I would say that on average, sales were increasing at a rate of $36,000 per year. Now, this part here says, does the data represent a linear function, and then explain. So the fast way to answer that is that if it's a linear function, then by definition that the sales should be going up or down. In this case it goes up the same amount per time period, and it's just convenient in the chart that we have some equal time periods here. So for example, here is a 5-year period, and going from 10 to 15 is a 5-year period. In fact, you could look at 5 to 10 as a 5-year period. So if you look at these 5-year periods, for this to be linear, then total sales would have gone up the exact same amount, not just close. And if you were just to compare a couple that are obvious, for example, going from 1.40 to 1.85, this says that sales went up 0.45, or if you just subtract those numbers, $0.45 million over that 5-year period, whereas in this 5-year period they only went up about $0.03 million. So not even close to being the same change over the same time period. So the short answer is just that this data is not a linear function. Is it a linear function? No. And the explanation would be that there is not constant slope. And then to phrase that in a less mathematical way, since we were giving a story context, you could say that there is not a constant rate of change. So if you want a more methodical mathematical way to prove that the slope is not constant, this is the idea. If you do indeed have a line, one could pick 2 points on that line and calculate the slope between them, and they would get the same slope here as if they were to calculate the slope for 2 other points on the line. That's the definition of a line, is that there's constant slope no matter what 2 points you pick. Suppose I was to make my first calculation being such, this is my x1, this is my y1, and this is my x2, and this is my y2 here. Then using slope, I would have y2 minus y1 would be 1.85 minus 1.40, and then in my denominator x2 minus x1 would be 10 minus 5, and that would be me calculating the slope between, say, these 2 points right here. And then if it were indeed linear, I would come up with the same thing as if I was to do the slope between these 2 points, say, further on, and that would be using, say, this as my x1 and this as my y1. So scratch this and scratch this. I would now make this my x1, and this my y1, and then this would become my x2, and this would become my y2. So picking 2 points further on the line, I would have that my y2 would be 1.88, and my y1 would be 1.85, and then in my denominator for slope would be x2 minus x1, which would be 15 minus 10, and that would be me calculating the slope between two other points on this proposed line. So this, if you were to take your calculator and subtract, you would get 0.45 divided by 5. And up here, you wouldn't get that, you would get 0.03. If you took 1.88 and subtract 1.85 on your calculator, you'd get 0.03. And then 15 minus 10 is 5. So you can do this calculation on your calculator and that calculation on the calculator, but isn't it clear just the fact that these have the same denominators and different numerators, that these are not the same numbers, meaning that this first calculation here, 0.45 over 5, is some slope here, and then what happens is over here, when you get further on, it's not the same slope. In fact, it's a very small slope. 0.03 divided by 5 is very small. So what would happen is between these 2 points, the line would bend like this. And in mathematics, lines have to have the same slope. It cannot change. So here would be a graph of a line with this slope, and here would be the graph of the line with, say, some very, very small slope.